Okay, previously we saw that any mechanical system can be uh, equivalently, it's analogous to electric system, and we can do the analogy in two ways. The first one is called as a force voltage analogy, and the second technique is right the force current analogy. In that way, we could represent. I think we solved the problem. No, we check that how what are the equivalent components when it comes to the force voltage, and what are the equivalent when it comes to the force current, right? Okay, now let's solve a problem. This question is draw the electric equivalent network based on this is force voltage analogy. Okay, the question. So this is the diagram. All right. Mass m1, we have in the spring, and mass m2, so this is a k2. Alright, so this is x1, this is x2, and let us say we have a b2 over here. Okay, so this is the given diagram. Sure. Our intention is that we want to convert this into its equivalent electric circuit, right? So whenever we want to do so, first step remains the same like our previous case. I need to write the differential equation, right? So first I have to get a differential equation. In order to get a differential equation, I need to convert the mechanical block diagram into the network, correct? right? Once we identify the nodes, as we know that this is a translational system, so displacements become nodes. So since there are two masses given over there, so corresponding to each of the mass, right, we already have marked the displacements. All right, so we can convert this into a network based on the mechanical components. We'll write the equivalent what you call equivalent differential equations, right? Replace the differential equations by their corresponding equivalent components of electric components for a given this thing. Okay, so that when we write that completely, we will understand, okay, what exactly has been given over here, how to convert the given equations into the electrical circuits. Okay, all right. So first objective is to write a mechanical network of the given system. I can see that the two nodes are x1 and x2, right? This is obvious because there are two displacements. So why only two displacements? Because there are two masses, right? Mass is the only component which, right, satisfies the requirement as that it's the whole mass will move, right, as a single body, correct? Because of that we are writing in this way. So I can see that x1 is connected to the following. So x1 is directly connected to b1, force is connected to that, k1 is connected to that, m1 is connected to that, and between what you call x1 and x2, right, I have k2 and b2, right? Only the m2 is not connected to x1 directly. So these many components I am supposed to mark now. Okay, so that therefore the first I'll write, say, a mass is m1. Then I have say a spring. This is k1. Then we'll write a damper. This is b1. We'll connect all of them to this node. Okay. Then between x1 and x2, we observed that there is a spring and we have a damper. Okay. X2 is connected to three components, b2, k2. Out of this is k2, this is b2, between x2, x1, and only connected to x2 we have a mass m2. This is connected. All right. Now uh, we have a force. Force is also connected to x1, connected in this way. This is a 50. Okay, I think this is the required network. So this is the reference. So we'll call it as a ground as our as per the electric terminologies. Will be the next step. We have to write the equations uh, relating the force and the response at each node. Correct. So at node x1. So first node, every component we have connected, right? We'll write the response. So first one, input is f of t. The input is equal to output. So in on the other side, I'm going to write first component, that is m1. Response is always in terms of, correct, t square x of t by dt square, plus there is a k, so this is k1 into x1, right, plus there is a b1, it's a differentiation, so dx1 by dt, plus, right, the k2 is connected between two nodes, it is x1 minus x2, that is a b2. It's in terms of the differentiation, correct? I can write dx, or I can write in even the other way. So d by dt of x1 minus x2, both will be. Now, wherever we have the differentiation happening, we can even write the velocities, because the dx1 by dt can be directly written in the format of the velocities. So first, let's convert the velocity over there, because when we have the velocities, we can directly convert them into the electrical network as per this rule. See, yeah, this one, correct. Right. So I want the voltage to be present, sorry, velocity to be present over there, right? Then we can convert it, correct? So we'll convert this into the required format. So that is the f of t keep as it is. This is f of t is equal to, now what are the changes that I'm going to make now? So I'm going to make a replacement like this. So where I find the, yeah, we will write the velocities now. So v1 is equal to dx1 by dt. Okay? And if you have a v2, that's a dx2, right? Yeah, so we can write this is dx2 by dt. That is velocity. So this implies, I know d square becomes dv by d square x of t by dt square becomes dx by dv by dt. It's a rate of change of velocity. So these are the changes we are going to make. Therefore, the f of t becomes equal to, let's write, this is m1 dv1 by dt, correct? Plus, if you simply have x1, how do you get x1 in terms of velocity? Integration, correct? So this is integration 0 to t, right? This is v1 of dt. Now b1 into v1. When I have k, it has to be an integration. So integration 0 to t, this is v1 of t minus v2 of t dt, right? And the last term plus, this is v2 into, the differentiation is nothing but v1 minus v2. So this is the equation which we, all right. So now you can convert this equation directly into the force voltage. So applying analogy, I'm going to get the following. So force is equal to voltage. And so we can see that M1, right, refer to the table which we had written over here. Sorry, not that, previous to this one. Yeah. So wherever I have M, I can write L. B can be replaced as R. K is 1 by C. Right, so just compare this equation. E of t is equal to m1, we have m is equivalent to L, so this is L1. No, velocity equal to current, right? Just check once. So this is di1 by dt, force voltage, right? Right, 1 by dt. Then there is a k1. K is 1 by c, so this becomes 1 by c1 into integral. This is 0 to t. Velocity is a current, so this is I1 of t dt, plus B is a resistance, so this is R1. V1 is I1. Okay, right. Plus there is a K. So this is K2. So K2 means second capacitor. Okay. So 1 by C2 integral. This is 0 to T. Right. This is I1 of T minus I2 of T dt plus this is B2. So that is a R2 into this is I1 minus I2. So call this is equation number 1. For every node, I am writing a differential equation, right? Converting into the required format, then applying the force voltage or force current as per the requirement. This is what has to be done, right? Now, let's go to the second node. At node x2. So the differential equation becomes there is a mass connected, so it's m2 d square x2 by d square plus there is a k2 difference between the node values. So this is x2 minus x1. Okay, then plus this is b2 into d by dt of x2 minus x1, right, equals to 0. There is no supply. All right. Now let us write the equivalent. Bring the voltage. Bring the velocities in place of x2. So this becomes m2 d v2 by dt plus k2 integration 0 to t. This is v2 of t minus v1 of t dt plus b2 into this is b2 minus v1 equals to 0. Now to this equation, let us apply the force voltage energy. So when we apply that, let's so this means what happens, m2 is a L2 is equal to current, so di2 by dt plus k is 1 by c, so this is 1 by c2 0 to this is I2 of t minus I1 of t dt plus B is a resistance, so this is R2 into I2 minus I. We checked one thing when we analyze the force voltage analogy. So every component that you are going to consider will be in series. So we can see in the equation, and this is directly derived from KCL. No, sorry, KVL. My mistake. Okay, it's a voltage, right? So since the voltage is the power is the supply, a voltage gets divided among the components because every component is assumed to be connected in series, right? So each node equation tells you what are the components. Plus every component will be in series, right? So that in case of the KVL, normally the KVL gets applied to the mesh, right? So mesh or loop, correct? So smallest loop is called as a mesh, that's why. So we are expecting the mesh equations here. So each of the equation which you have written so far, like equation 1 and let's call this is equation 2, right? they will be the mesh equations. Okay, so we know that in a mesh, for example, let me write something. So I have a mesh here, and you can have another mesh over here. So there, these components are the shared components, right? They will appear in both the equations, correct? So if you have a resistor over here, a resistor over here, and another resistor here, so resistor here and resistor here, let's say. So if you apply a mesh equation here and here, this component is going to be appearing in both the equation, correct? So if at all you observe some components which are present in both the equations corresponding to x1 and x2, which we have written so far, right, that indicates those components are the common components between the two meshes, right? So let's check whether we have any such components now. Yes, correct. So I can see, yeah, I think we have the component. You see here, this is R2, this is R2, right? R2, same term, R2 into I1 minus I2, because you are applying the equation to the first loop. R2 into I2 minus I1, it's obvious because the component is present in the second, right? Assume we are writing the equation for the second one, and this is a common component, right? So just check this 1 by C2 and 1 by C2. Right, 1 by C2 I2 minus I1 in the second equation, 1 by C2 integral I1 minus I2 in the first equation. Again, right, it's a common one. So the other components what we are writing, they are not present as a common component. See L1 C1, this is L2 on the other equation. So the L1 C1 and is only present in the first loop, right? That's what we right now. So there is an inductor. To start with, we have an inductor followed by a capacitor for the equation 1, right? And this is supplied by a voltage source, plus minus. Okay, then also I can check that there is a R1, right, in the first equation. So first equation shows three components, L1, C1, R1, right? These are the components only present in the first loop, right? Then I should write C2 and R2 as common components. So right. So correct. So this is, there is resistor. Okay, so this is the common one, and in the second one we just have an L2, right? So this is the E of T. This is 1 C1. This is L2 C2 R2 R1. So whatever currents we measure, we are assuming this to be the I1, and this is I2. So they have to be opposite in direction because we always are writing I1 minus I2 or I2 minus I1. So when we write the equations, when we mark the currents, it is expected to be in the opposite directions like this. All right. So this is the answer. Please go through this once and let me know if you have any doubt. Okay. Fine. All right. Now, okay, let's go to another question that's based on current, uh, equivalent of the force current. You can even write the torque current, correct? Because anyway, yes, we know that force is equivalent to torque, and displacement equal to omega, and so on, correct? Omega is equal to, we can write E of T, the voltage, torque is current, and other terms. Okay, first let's write a question now. Then we'll convert that into the required format. So this is the question. The question is, yes, we will. Right, 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 right. So according to that, we have to make small changes. All right. Okay, this is the question. Obtain uh, electric network based on its TI. Okay, torque current analogy. So it's easy to obtain the torque current because force to torque conversions are very straightforward. Correct. So replace every force term by the equivalent torque term. Keep the right hand side same, right? So in this particular table, right? This is force voltage, sorry, force current. Replace the force. This is a torque, right? So we know that velocity becomes equal to omega, right? Angular velocity, correct? So mass is equivalent to the inertia, right? So B remains B, K remains K, right? So this, if you relate this with the right hand side, right, that becomes the torque current. Only this is what we need to do, right? Equation wise, there will be small changes, right? Okay. Ah, yes, yes, right. So every term becomes equivalent to. So you have displacement in terms of angular displacement. So you have a theta coming. So this is the question. This is T. This is how the T is applied. So this is J1 B1. So we have response theta 1 K1. This is J2 uh, B2, and this is theta 2 and K2. All right. So now our first approach is to write the equivalent network, right? So the mechanical network looks like this. So uh, yeah, what are the nodes here? Theta 1 and theta 2, right? So let's mark them. This is theta 1, this is theta 2. So connected to theta 1, we have the input. Yeah. So G1 and B1 are directly connected to theta 1. K1 is between theta 1 and theta 2. All right. And theta 2, I'll mark the, and we have J1 over here and B1, right? Okay. Okay, then on the other side we have connected to J2, uh, theta 2, we have a J2, J2B, yeah, B2. So we have K2, correct. So this is B2, this is K2, K1. So we have B1 and the supply is to theta 1, right? So this is capital T. Now, uh, fine. So let's write the equations, right? At node theta 1. This is the input is capital T. You can write T of T is equal to, this is B1 d theta 1 by dt plus J1 into d square theta 1 by dt square plus a k into, this is theta 1 minus theta 2, right, is the equation. Now the substitution that we are going to make now in terms of, because we had displacement, we converted into velocity. Now the angular displacement should be converted into angular velocity, right? So we use omega 1 of t is equal to d theta 1 of t by dt, and the omega 2 will come into picture wherever we see d theta 2 by dt, correct? So corresponding to the angular velocities of the those masses which are connected. Okay, uh, uh, inertia, sorry, not mass. J1 and J2 will have the angular velocities like this. So converting them into the required format after the substitution becomes equal to, left hand side is t, no change. The on the right hand side we have b1 d theta 1 is omega 1 plus j1, it's a d square theta 1, so out of which d theta 1 by dt is omega 1, so this is a differentiation of omega, so d omega 1 by dt. I think this is k1, I'll update. So this is k1 into, it's just theta, so from omega if you want to get back to the theta you should integrate, so this is integral 0 to omega 1 of t minus omega 2 of t dt, right? This is the equation number. Okay, before let's directly apply the uh, torque current analogy. So this is by applying the ti analogy we get, so torque will be replaced by the current, so this is t of t, right? So in current analogy we know that input will be a current, so this is the current source connected. Okay. Should be equal to, if you compare the b1 and r1 are equivalent, is it, one second, let me just verify. Yeah, so b becomes 1 by r1, correct? K becomes 1 by L, B is 1 by R, mass equal to capacitance, right? Mass in the sense the J becomes equal to capacitance, omega is E, torque is I. Okay, so let's have is now 1 by R1, omega 1 is nothing but the E1 voltage, plus J1 becomes equal to C1, uh, yes, So this is omega equivalent to voltage. So this is dE1 by dt. K in force current, it is I one. Sorry, not I. K is 1 by L. So this is 1 by L1 integral 0 to t. Omega is E. So this is E1 of t minus E2 of t dt. So now we'll call this is equation 1. Equivalently, now we'll at node theta 2, let's try to write the equation first. So we can see that J2, B2, K2 are connected and K1 is between theta 2 and theta 1. So the differential equation is J2, this is B square theta 2 by dt square plus this B2 d theta 2 by dt K2 into theta 2 plus this is K1 theta 2 minus theta 2. For the second one, there is a no supply. So we want to write that, convert the theta into omega, right? So applying that, this is J2 into this d omega 2 by dt plus this is B2 into differentiation of theta 2 gives you omega. So this is omega 2 plus K2. Theta is integration 0 to t omega 2 of t dt. Alright, plus K1 integration 0 to t omega 2 of t minus omega 1 of t dt, right, equals to 0. Okay, just verify this equations. So once we have this, now I think we can directly apply the torque current equation, right? So this is by applying the TI analogy to the above equation. Let's just verify once. J is a C, so this is C2 d E2 by dt plus omega 2 is E2, B2 is resistance, so 1 by resistance plus, that's an equation for current, so K2 becomes 1 by L2 integration E2 of t dt plus 1 by L1 integration 0 to t E2 of t minus E1 of t dt, right, equals to 0. So call this as equation number 2. We want to consider the following. Let's compare the equation 1 and 2 first, just to decide whether there is a common component. If you have uh, difference of voltage, then that's a common component. All right. So E2 minus E1, sorry, 1 by L1 E1 minus E2, 1 by L1 E2 minus E1. Yeah. So L2 is common. Again, we have to decide something more here, whether you are going to write in series or not. You have to decide. That depends upon what analogy you are using. If you are using a voltage, we know that voltage gets divided when the components are in series. But now this is a current analogy. So under what condition? Yes. So when you apply a input current, right, to a node, current gets divided only in the parallel branches. So the equation number one, you can see that the input is a current. So this current should pass through these three branches, is the meaning, right? One branch has resistance, one branch has capacitance, the third branch, which is between the two nodes, will have inductance. Okay, so it depends upon the analogy. So as soon as see that there is a current analogy, I should understand that the circuit which I'm going to write will have parallel branches. Okay, the components are not in series. Every component will be present in the parallel format. So for that reason, let's so now the what you call node gets replaced by E1. Okay, so one node has a node voltage E1. This is node analysis, not the mesh analysis. So the previous one was loops, right? So we used to write now it becomes the node analysis. Equations are corresponding to each node. So at node 1, we can see that there we have two components, right? One is a resistor and one is a capacitor. One resistor, one capacitor in parallel. Okay, and between the nodes, we can see that there is a component which is a inductor. So this is R1, C1 and L1. So we'll look at the node 2 now. So equation corresponding to node 2. Anyway, we understood that this component is a common component we already have written. And then the parallel components are corresponding to only E2. If you have just E2, that's corresponding to this node. Right? We can see that C2, R2 and L2, they are in parallel. C2, this is R2, this is L2. So those three components are in parallel and C2, R2, L2. Okay, now where is the supply? Supply is in terms of current source. This is the supply. So as per our notation, this is the I of t. I of t. So the current that is entering here initially gets divided into this. Then whatever currents enters into this flows through the three different paths. So that's the meaning of the equations. From the equation itself, I am able to write this. Now, see, I'll give you two homeworks to work on this. This is important. We get many situations where we need the interconversions. So just practice this. All right. This is homework number 1. Okay. The question is draw the electrical network based on. Okay, we have done force voltage already, so I am going to ask. So this is force current. Okay, apply Fi analogy. Okay, that's the question for this. This is B2, K2, M2, f of t, and this is the reference. So the question is apply Fi analogy, force current, to convert this block into an electrical network. Then I ask, okay, the question which we solved is torque current, correct? Yeah, so I'll ask a question on torque voltage, the other option, right? So that we solve all the four types in this, okay? This question is the TV, torque voltage analysis. K1, B2, theta 2, this is B3. Theta 1 has to be assumed here, right? It's left to us. Okay, we have to assume. No, there is no J. Huh. Yes, yes, yes. You can see that there will be a theta 1 here. So other end of K1 there should be a theta 2, correct? So they may not give the theta value. We have to assume. Okay. Now, so we try to represent the system in terms of block diagrams now. Okay. So this is the block diagram. So let's look at some examples, right? Why do you, how can you represent uh, a system using a block? What we are going to write inside the block? Let's consider two examples. All right. The first example, I have say two voltage sources, and let's keep the circuit very simple. Let me consider only one resistor. This is V1, this is V2, and this is the resistance. Okay, now because of this there is a output, that is current. So voltages are the inputs here, okay, and the current is the output. Now see, I'll try to convert this into the equivalent block diagram, right? So as I know now, when I write a block diagram, what you are expecting? You are expecting input on this side, output on the other side. So the let's assume that the total voltage across a resistor is V. So V should come here, correct? And what is output? Current. Right? So if you want to write a current equation for resistance, what's the equation? I is equal to Vy, V by R, correct? So what is V in this case? This voltage is V1 plus V2, right? By R. So it means V1 and V2 are the input variables. You have to add them up. So this is plus. From one side you give V1, right? From the other side you give V2, correct? So both are plus. V1 plus V2 comes here as V, right? This V is V1 plus V2. What you should write here in this case? What should be written inside this block, right? I have V. No, V1 plus V2 is what I'm getting here because already I used a summer block, that's plus, which is you. Yeah, inside this what I should write, so that you get a I on the output, I at the output side. V is there, divide by R. So this is 1 by R. Now you see, you converted a circuit into the block diagram. Very simple approach, right? So this indicates that yes, we can convert anything, right? Any circuit into a equivalent block diagram. So now we are just introducing the block diagram concept, right? So I'll go for another example. Okay, so this one is fine, right? Let's go for a different one. Say, let's look at another circuit. So we have two resistors, and say I have one voltage source plus minus V. Let me connect in this way. All right, so let's assume the names of the resistors are R1 and R2. Okay, now I know that there will be the outputs. What are the outputs? Right, V is the input voltage. R1 and R2 are the two resistors connected, indicates that there will be a current I1 and I2, correct? Right, so now you see, right, we have input voltage. So what I'm looking here, I'm looking, right, V as inputs and two outputs. So this has to be in the only in the following fashion. I cannot write in any other way, right? Because I have two outputs. I1 is one output, I2 is the other output. So in this case, one input, two outputs. What should be written inside the blocks? Right. So this is 1 by R1, and other one has to be 1 by R2. So very straightforward, right? Any circuit, right? Again, we can add up many more components to this circuit so that we can write the complex blocks. All right. So but anyway, since our intention here is to just to verify whether you can convert a circuit into the block diagram, right? Because just now we understood that any mechanical system can be converted into electric. So now we understood that electric can be written as a block diagram. So this means anything, either electric or mechanical system, can be directly represented in in the form of a block, right? Multiple types of blocks can be used, and we can represent any given system. So the next concept will be introduction of the feedback and concepts related to feedback, and then we'll look at the uh, different operations with the block. Then we'll go for the block reduction techniques. Okay. So that's what is going to come up in the next few classes.